Hi, let's continue with the spectral theorem. As an application of spectral theorem, let us give some applications to geometry, coordinate geometry. Let us begin with a very familiar theme that you have studied in your class 12th. Conics, ellipses and hyperbolas are examples of central conics. And you have studied these conics with standard equation x squared upon a squared plus y squared upon b squared equal to 1 and x squared upon a squared minus y squared upon b squared equal to 1. Now let us consider a slightly different type of a locus, x squared plus y squared minus xy equal to half. Just clearing the denominator, 2x squared plus 2y squared minus 2xy equal to 1. What kind of a locus is this? Is this locus an ellipse or a hyperbola? Let us examine this problem. Let us write this equation 2x squared plus 2y squared minus 2xy equal to 1 in matrix form. It reads row vector xy, symmetric matrix 2 minus 1 minus 1 2, column vector xy. I'm sorry, this must be an xy. There's a very minor typographical error. So it is natural to subject this column vector xy to a rotation of coordinates. So xy equal to cos theta minus sin theta cos theta, capital X capital Y. Correct? Or let us write little x little y as p times capital X capital Y, where p is an orthogonal matrix. Orthogonal matrix determinant 1. What happens? How does the equation transform? The equation transforms to remember little x little y is p times capital X capital Y. So it will be capital X capital Y row p transpose AP capital X capital Y column equal to 1, where A is the matrix 2 minus 1 minus 1 2. Now we must choose. Now so far we are completely at our we have the freedom to choose this orthogonal matrix in whatever way you want. But now notice that this matrix A has eigenvalues 1 and 3. It is a real symmetric matrix with distinct eigenvalues 1 and 3. Take the corresponding eigenvectors v1 and v2, and we know that v1 and v2 are going to be orthogonal. I can divide v1 by its length, divide v2 by its length, and I can assume that v1 v2 is an orthonormal pair of vectors, and I can replace v2 by minus v2, and I can always assume that this matrix P, which is obtained by stringing this v1 and v2 together, is an orthogonal matrix. I can also assume its determinant is 1. So orthogonal matrix 2 by 2 matrix with determinant 1 is a rotation of the plane through angle theta. So now this particular matrix we shall work with, and then what happens? Then we know that if we choose my P to be this particular orthogonal matrix, then P transpose AP simply becomes the diagonal matrix. The diagonal entries 1 and 3. So this new equation, or the transformed equation, becomes xy diagonal 1 3 capital X capital Y equal to 1. Or write it out, capital X squared plus 3 times capital Y squared equal to 1. Obviously this after rotating the coordinate system, we see that we get an ellipse with major axis, semi-major axis 1 and 1 upon root 3. Where is the major axis aligned? Along E1 cap. Where is the minor axis? Along E2 cap. So capital X capital Y. So the major axis and minor axis in the capital X capital Y coordinates are E1 cap and E2 cap. So what are the major and minor axes in the original coordinates little x little y? Remember, what is the relationship between little x little y and capital X capital Y? Little x little y is P times capital X capital Y. So when I take capital X capital Y to be E1 cap, that is the major axis in the new coordinate system, I will get the I'll get little x little y, which is the coordinates of the major axis in the old coordinate system. But capital P applied to E1 cap is the first column of P, remember? So the major and minor axis in the original coordinates are PE1 cap and PE2 cap, but PE1 cap is V1, PE2 cap is V2. So we see that this particular locus 2x squared plus 2y squared minus 2xy equal to 1 is an ellipse. We know it's an ellipse. We know what is the major axis. We know what is the minor axis. We know along which what is the direction of the major axis and what is the direction of the minor axis. Namely, the major and minor axis are along the eigenvectors v1, v2 respectively. You can calculate the area of the ellipse and you can do other geometry with it. So this is one instance of how the spectral theorem can be used. Now you can do the same thing with ax squared plus 2hxy plus by squared equal to 1. That's a conic. Under what kind of condition, under what conditions will this conic be real? Now remember that the eigenvalues happen to be 1 and 3. What if the eigenvalues happen to be minus 1, minus 3? Then I would have gotten minus x squared minus 3y squared equal to 1. There are no real points x and y satisfying minus x squared minus 3y squared equal to 1. Then I would have said that the locus is empty or the locus is not real. It's imaginary. So under what conditions on A, B, and H is it that this particular conic has real points? That is, it is a real locus. When is this locus an ellipse? When is this locus a hyperbola? And if in case it's an ellipse, what is the area of the ellipse? These are the questions you can do. And the same thing you should go through. Little x, little y is capital P times capital X, capital Y. You should choose the columns of P to be the eigenvectors. And then the new equation is going to be lambda capital X squared plus mu capital Y squared equal to 0, where, lambda capital X squared plus mu capital Y squared equal to 1, where lambda and mu are the eigenvalues. If both lambda and mu are negative, the locus is not going to be real. If lambda and mu are both positive, it's going to be an ellipse. If one of them is positive, the other one is negative, it's going to be a hyperbola. So you know how to do this problem. So I'm leaving it to you to complete this problem. So now let us take the next example. Let us take a 3 by 3 real symmetric matrix. 2 minus 2 minus 1 minus 2 5 2 minus 1 2 2. You can write the characteristic equation x cube minus trace times x squared plus sum of the 2 by 2 principal minus times x minus the determinant. So when you do that, you're going to get x cube minus 9x squared plus 15x minus 7 equal to 0. So this factorizes. In fact, I had chosen the matrix in such a way that you get nice factorizations. X minus 1 the whole squared into x minus 7. So the eigenvalues are 1, 1, 7. It's a real symmetric matrix. A real symmetric matrix is diagonalizable. You should be able to find 3 linearly independent eigenvectors. So when you take lambda equal to 1, you have to solve A minus lambda I equal to 0. So this is the matrix applied to x equal to 0. So you must perform row operations. And you will see that the rank is 1, the nullity is 2. And so you're just left with one equation, x1 minus 2x2 minus x3 equal to 0. And simply by inspection, you may be able to write two vectors, v1 and v2. v1 and v2 are both eigenvectors with eigenvalue 1. They are not orthogonal, but you can make them orthogonal using the Gram-Schmidt. So you divide the first vector by its length, namely root 2. So w1 is 1 upon root 2 times 1, 0, 1. The second vector, you apply Gram-Schmidt and obtain it. 1 upon root 3 times 1, 1 minus 1. So you got these two eigenvectors, w1 and w2, with eigenvalue 1. Now with eigenvalue 7, again a minus 7i x equal to 0. So you have to subtract 7 times the identity. You will get this new matrix minus 5 minus 2 minus 1, minus 2 minus 2, 2, minus 1, 2, minus 5. You have to perform certain row operations. This time the rank is 2, the nullity is 1. There's 1, and then you can get a solution, a non-trivial solution, minus 1, 2, 1. You normalize it, so make it a unit vector, 1 upon root 6. So I got 3 orthonormal unit vectors which are eigenvectors, w1, w2, and w3. String them together and you get a matrix O. Here the O is not the zero matrix. O is because it's orthogonal. O for orthogonal. When you string these 3 unit vectors together, orthonormal unit vectors together, you get an orthogonal matrix O. O transpose AO is the diagonal 1, 1, 7. So now let us consider the locus. This time I'm going to take this matrix. What is the matrix again? The matrix is this matrix. I'm going to take xyz column and xyz row, multiply them out. I'm going to get a quadratic. I'm going to get a quadratic in 3 variables. So this is the equation: 2x squared plus 5y squared plus 2z squared minus 4xy minus 2yz plus 4zx equal to 1. What kind of an object is this? This is an object in the surface in 3-dimensional space. This last equation, this last displayed equation here, is a surface in 3-dimensional space. Is it a sphere? Is it an ellipsoid? Is it a cylinder? What kind of an object is it? Again, to investigate this, we should write it in matrix form. Little x, little y, little z, A, little x, little y, little z column equal to 1. Again, I'm going to how do I identify the nature of the locus? I must subject it to an orthogonal change of coordinate. Little x, little y, little z is an orthogonal. It will be O times capital X, capital Y, capital Z, where O is an orthogonal matrix. So substitute this into the equation 1. What do you get? You get capital X, capital Y, capital Z rho O transpose AO, capital X, capital Y, capital Z equal to 1. Now, how should you choose O? We are just taken this O. Remember, we got a O. The convenient O that I'm going to get is this O. Why am I chosen this O? Because O transpose AO is diagonal. That's the reason. So if I choose that particular O, the equations become simple. It is 1, 0, 0, 0, 1, 0, 0, 0, 7. So the new equation of the locus is x squared plus y squared plus 7z squared equal to 1. Had it been x squared plus y squared plus z squared equal to 1, it would have been our good old sphere. But this is a sphere which is elongated. An elongated sphere is called an ellipsoid. It's an ellipsoid with semi-axis 1 upon root 7. What are the axes of this new ellipsoid in the new system of coordinates? E1 cap, E2 cap, E3 cap are the directions of the principal axis in the capital X, capital Y, capital Z coordinates. So what are the directions of the principal axis in the original coordinates? Remember, little x, little y, little z is O times capital X, capital Y, capital Z. So when I put capital X, capital Y, capital Z, when I choose to be E1 cap, E2 cap, or E3 cap, I get the corresponding columns of O. So the directions of the principal axis in the original coordinate system are the 3 eigenvectors W1, W2, W3. So finding eigenvalues and eigenvectors for a real symmetric matrix tells you many things. If you construct the locus x transpose AX equal to 1, you can decide what kind of a locus is it. Is it an ellipsoid? Is it a hyperboloid of 1 sheet? Is it a hyperboloid of 2 sheets? What exactly is it? That is a kind of a question you can answer. If it in the case of an ellipsoid, you can find the volume of the ellipsoid and so on and so forth. So these are some nice applications of spectral theorem to geometry. You can deal with any quadric surface: ax squared plus by squared plus cz squared plus 2hxy plus 2gxz plus 2fyz equal to 1. This can be brought to the form lambda x squared plus mu y squared plus mu z squared. Lambda, mu, nu are the eigenvalues of this matrix, of this 3x3 real symmetric matrix, subjecting it to the change of variables and so on. If lambda, mu, nu are all negative, the locus is imaginary. There is no real locus. And so the interesting case is when at least one of lambda, mu, or nu is positive. Say I'm going to assume that lambda is positive. All 3 are positive. It's an ellipsoid. If one of them is, if 2 of them are positive and one of them is negative, it is a hyperboloid of 1 sheet. If one of them is positive and 2 of them are negative, it's a hyperboloid of 2 sheets. If one of the eigenvalues is 0, the locus is a cylinder. So now you might wonder, what is the picture? Ellipsoid, I'm sorry, I'm not very good at drawing pictures. Here is a picture of the ellipsoid. It's just an elongated sphere. You can get a beautiful picture of the hyperboloid of 1 sheet. Let me see whether I can get it for you. You see here is a hyperboloid of 1 sheet. You see, this is a hyperboloid. Let me give you another picture of the hyperboloid. You see? Here is a picture of the hyperboloid of 1 sheet. You may have noticed some of these street vendors, carrying a moda made of cane. It looks exactly like this, and he has a plate, a huge aluminum plate, which he places on top of this moda, and he keeps his eatables on that to sell. You see, the structure is very. This is a very robust and stable structure. You can create this hyperbola out of one sheet with two families of lines, and those cane sticks that you see in this moda are exactly these lines. So, in fact, the Russian engineer Shukov actually used this idea to construct a tower. This is called the Shukov Tower. This is a Shukov Tower in Russia, actually. And I'll give you, this is from the Wikipedia, and let me give you the exact reference. Is given the Shukov Tower in Polybino, and this was built, I think, in 1896 or something like that. So here are some exercises on identifying these exercises will be taken up in the next tutorial class. These exercises will be taken in the next tutorial class. I already given the. I'm going to put this up in the Moodle very soon. So with this, I'll stop this capsule, and the following capsule are a few odds and ends, and there are 4 pages of notes, and they're optional. The next capsule is an optional capsule. So this capsule I'm going to stop here with some nice calculations and applications. Thank you.